Thank you, everyone. Welcome to my presentation on benchmarking quantum computers using Bell tests. And so this was done under the help of Dr. Sergey Strelchuk. He's a teacher here at Cambridge, or professor, sorry. Yeah, so here's a quick overview of the presentation today. I'll be going over what quantum computing is and qubits. I like to think that in pop culture, quantum computing is used so loosely that no one really knows what actually goes on. So get prepared for a quick crash course. Then going into testing quantum behavior using Bell inequalities. And for our research, we use two types of Bell inequalities, the Mermin and Svetlishny, which I'll be going in depth into. And I'll be talking about preparing and measuring entangled quantum states. So this is like the core of what we did in our research. And then also the impact of noise on quantum tests, and then the results of my research, and then future directions of quantum benchmarking research. So first, an introduction to quantum computing. As you all know, classical computers make up like 99.9% of all computers in the world, and they all have one fundamental property that's unique, that's shared among, is that they use bits, which is the most fundamental piece of information a computer can process. It can be either 0 or 1. It can be true, false, electrical input, no electrical input. And so the difference here is that quantum computers use qubits. And so qubits can also be either 0 or 1, but then sometimes it can also be both. And we call this a superposition of state. Another thing qubits can do, which are unique to quantum computers, is that qubits can intertwine with each other. And we call this entanglement. So what that means is if I have two qubits with me here, I can intertwine them in such a way that I can put maybe an X amount of distance between them, and the state of one qubit immediately affects the state of the other qubit. So those are some of the quantum properties that give quantum computers such an edge over classical computers. And so this then begs the question, how do we know if a system is truly quantum? So let's say in the future, maybe 50, 100 years from now, let's say we're all using our quantum computers. Well, how do we know we haven't been scammed? It's a bit of a bleak outlook, but quantum computers are really, as per human engineering right now, are really susceptible to noise and interference. And so as a result of noise and interference, quantum devices can behave classically. And classically, I mean just like a regular computer. And so all the advantages of a quantum computer are essentially erased as because of interference, you're just stuck with a regular old computer and losing out on quantum advantage. And so we need an objective test of quantumness. And so to find and create this test, I'd first like to introduce you to John Bell and his theorem. In '64, Bell proposed a theorem to distinguish quantum mechanics from classical physics. And you see, classical physics is derived under two main assumptions, locality and realism. And so what locality is this concept. It's a really simple concept, both locality and realism, is that what happens in what one object does and another object does, they cannot have any instantaneous effect on each other. So for example, if I flip a coin here, and let's say Oliver on the other side of the room flips another coin, there's no way those two coin flips can affect each other instantaneously. And so it's an extremely simple concept. And then realism, again, it's this idea that objects have predetermined qualities. So again, if I go back to the coin flip analogy, if I flip a coin and cover my wrist on where the coin is, whether it's heads or tails is already determined, right? It's not in some sort of state where it's both. It's either heads or tails. And so realism is this idea that objects have predetermined qualities. And so the genius of Bell's work was that he managed to draw limits, mathematical limits that we could apply to the real world to these classical assumptions. And so this led to the formation of Bell inequalities, limits that classical systems cannot exceed. And so the violation of these Bell inequalities reveals quantum behavior. So this kind of directly applies to my research. And so then how can we harness the power of Bell inequalities? Well, as I said again before, Bell inequalities are a family of mathematical inequalities that have a classical and quantum bound. And so when you break the classical bound, it's the first signal that there is some sort of quantum behavior going on. And then how close a device can get to the quantum bound using its qubits implies, again, how quantum it is. I know I've said quantum a couple times, but I'm going to say it more, so get used to it. Sorry. And so then based on how close it can get to the quantum bound, it allows us to make comparisons across different quantum computers. So, as I said in the overview, during my research, we looked into two of inequalities that we can use as tests of quantumness. And so the first one is the Mermin inequality. And this is a Bell inequality designed for 3-qubit systems. And what that essentially means is that, let's say I have a quantum computer I want to test this on, and it has 128 qubits. I pick 3 of those qubits to test. And so the classical bound of this inequality is 2, and the quantum bound is 4. And what this does is checks if the particles are entangled. And so the violation proves that the system is non-local. If you remember my definition of locality earlier, if one coin flip, let's say our qubits are coins, a coin flip here should affect the coin flip in another room. And so the violation of this inequality proves the system is non-local. And so allow me to try explain this formula to you. Although it looks theoretical, it should be quite simple to understand. So on the right-hand side, you see A, B, C. Those are our 3 qubits, Alice, Bob, Charlie. And those hats over each represent a measurement. And so what are they measuring, right? So because measurement is relative to something. And you can see the subscripts of each letter, A1, A2, B1, B2, and so on. And what what 1 says is that we are using the Pauli X operator, and that is what we're using to measure. And so what is the Pauli X operator? Well, if you imagine with me for a second a 3D plane, so an X, Y, and a Z axis, then applying the Pauli operator is to say, well, how aligned is my qubit with the X axis? You see, in 3D planes, we can envision qubits as a vector. And so by applying this Pauli operator measurement, what we're asking is how aligned is this qubit vector with the x-axis? Similarly with the Pauli y, how aligned is it with the y-axis? And so these operators return values that we tensor product together. And so you see these triplets of values that we sum and subtract from each other. They're expression values. And what they signify is taking a measurement of 3 qubits simultaneously. And then we add and then subtract to get our Mermin value. And then we have the Svetlishny inequality. And essentially what this is a stricter version of Mermin. Again, designed for 3 qubits, the classical bound is 4, and the quantum bound is 4 root 2. And what I mean by a stricter version of Mermin is that the violation of the classical bound proves that the system is genuinely tripartite non-locality. And what that means is that there's no mix of classical and quantum qubits that can break the classical bound. So let's say I have 3 qubits, one of them acts quantumly while the other 2 act classically. Then there's no way for those 3 set of qubits to break the classical bound. And so the Svetlishny inequality is just a stricter version of the Mermin. And here, in the same notation as described, the Mermin is the Svetlishny inequality. It's a bit longer. Yeah. And now we have the Greenberger-Horn-Zeilinger state. So again, this is a bit more theory. Couple more theory slides, so try not to take a nap. And what the Greenberger-Horn-Zeilinger state, GHZ state, is that it allows us to have our qubit system and maximally entangle it. And so what this does is that it gives the quantum computer the best opportunity to prove that it can act quantumly. And so to give an analogy of why we do this, let's say we have an orchestra in this room, and we want to prove that this orchestra is the best orchestra in the world and can play together in no other way any other orchestra can do. Well, you would provide a piece for them to play that proves that they can do this. And so our GHZ state is essentially this classical music piece that we give to our qubits that allows them to fully show their colors and that they're quantum. And so this is the ideal state for testing quantumness. And so now it's time to go over noise and its impact. So contemporary quantum computers today, even like with the best human engineering, all have their imperfections. And this causes noise or interference. And so some sources include decoherence, gate errors, readout errors. And as you all must know, quantum computers operate at sub-zero temperatures. And so no matter how accurate we get our engineering to be, as disappointing as it is, there's going to be some sort of errors and issues with our qubits. And so noise can essentially reduce and mask quantum correlations, and measured values for the breakage of these inequalities are reduced. And so observed quantumness is reduced. And so now we go on to the research that I've done, building a quantum test. We use the penny lane framework to build and optimize our circuit, and the default.qubit simulator allows us to emulate quantum computers. This was done in Python, a programming language. Then we use this, I managed to program this circuit with the GHz state. And so how this is done is penny lane offers a variety of installments and essentially features that allow us to simulate this. And so we can easily compute and create these inequalities and get the attained value for each set of noise level. And so as seen in the last line, we repeatedly perform these tests under different noise profiles and then different noise strengths so that we can evaluate the strength of the inequality against interference. And so here's the result. Here we have depolarizing noise. And so what this kind of noise is that it emulates it emulates, like, for example, it's kind of like a random error noise. So what it does is that with our qubit system, it just randomly, the strength symbolizes the probability of this happening, and it just randomly erases qubit, and it's sort of like a forget kind of thing. And the qubit state essentially just forgets what's happening. And that's the effect of depolarizing noise. And as seen with the Mermin inequality, small strengths of either like roughly 0.15 show that the Mermin immediately falls back into classical ranges, showing us that the quantum computer acts classically past the strength of depolarizing, showing how depolarizing noise is very damaging to quantum systems. Next, we have bit flip, and this is sort of symmetric noise systems. And what this does is that with our qubit state, it flips what the probability of the state being in 0 and the probability of state being in state 1, and flips it so that it causes this error. This can be seen in gate errors, and so it causes this symmetric curve. As if you imagine, if we have all the time bit flips, then it's essentially like doing nothing. It's like flipping once and then flipping once again. So as you see here, we get a beautiful curve showing the effect of bit flip. Next, we have phase flip, and instead of switching and this is essentially the same as bit flip, but instead of switching the integers, so the state of probability of being in state 0 and the state 1, it switches the probabilities instead. So this has a much more damaging effect, but ultimately we can see a recovery later on. And so this is again another type of symmetric noise. Next, we have amplitude damping. So this models energy loss. So for a qubit to be in state 1 and not state 0, it needs to be in an excited state. And so what amplitude damping does is that it simulates energy loss. So the state of it being in state 1 decreases as the state of it being in state 0 increases. And so as seen with the Mermin inequality, we see that it starts to go below the classical bound and stop acting quantum at roughly 0.375. And this shows the effect of amplitude damping. And then finally, we have phase damping, which is, again, the similar effect to amplitude damping, where instead of modeling energy loss, it models phase. So for example, if we have the state of a qubit being in 0 and 1, instead of switching the probabilities, it switches whether the symbols are positive or negative. So as in quantum computing with qubits, the probabilities are also displayed as imaginary numbers. And so these imaginary numbers can be either positive or negative. And what phase damping does is it switches the positive and negatives around, causing an asymmetric noise effect. And we can see here it's roughly 0.375 when the Mermin inequality starts to show the quantum system as a classical system. So yeah, a quick summary of all these graphs is to show that the Mermin inequality, although it is susceptible to noise, it only starts allowing the computer to behave classically at a noise strength of roughly 0.2 to 0.4. And so this directly contrasts with the Svetlishny inequality, where I won't explain what the noise sources do, but you can see that the portrayal of quantumness starts immediately decreasing at roughly 0.1. And so this is common throughout the Svetlishny inequality, with exception to the symmetric noise sources. So as seen here, if you remember what the Mermin curve looked like, you'd remember that the Mermin only started to dip below the red line at roughly 0.3. And so this essentially makes sense, as the Svetlichny inequality is much more stricter than the Mermin. And so its strength against noise and ability to withstand it is much less than the Mermin. And so it's a similar curve throughout. And here's phase damping. And so a quick summary of the Svetlichny inequality. You can see compared to the Mermin that it's, again, I'm repeating myself here, but it's much more weaker to noise. And it immediately shows the system as classical at roughly 0.01-ish. Yeah. And so conclusions of this experiment and this research are that the Mermin inequality is more resilient to noise than the Svetlichny. And what that shows is that the Mermin inequality is a much better test of quantumness than the Svetlichny. Then noise sources are important to address in future development, are depolarizing, phase damping, and amplitude damping, as these are asymmetric noise sources. And that's not to say that bit flip and phase flip aren't necessarily needed to address, but we can address these later on. It's just depolarizing, phase damping, and amplitude damping are really important to address, as they have more devastating effects on quantumness tests. And then Bell tests are a valid method of confirming quantumness, as seen with the research done. And moving forward, how can we continue to research into this area of benchmarking quantum computers? Well, we can attempt to include other inequalities. If you notice that our inequalities here specifically targeted 3-qubit systems, there's some other inequalities like the MABK, which target an n number of qubits, and where the classical and quantum bounds increase exponentially with n. And so if we manage to include much more bigger inequalities, then the ability to evaluate bigger quantum systems becomes much more easier. And then we can try to test this on real quantum computers, such as the ones offered by IBM, Amazon. And then we can also explore the use of error mitigation techniques to improve our measured violations, and so that we can ensure that, okay, let's say I have a quantum computer in the future, and I want to ensure that it's behaving the most quantum it can, given its noise profile. I can compare what its attained value is with the results achieved in this experiment and say, okay, it's achieved the same value, hence I know that despite the limits of human engineering, the qubits are of the highest quality. And so following this, we can truly be certain that we are harnessing quantum computing and quantum mechanics and not just using expensive classical machines. Thank you all very much. Q&A.
Especially with regards to, future, and also avoiding around like quantum was definitely a potential issue with the growth and rise of this technology. And just to kick off the Q&A, I just wondered, in your opinion, obviously quantum technology has become more and more important. There's hubs in Imperial, there's hubs around Oxbridge. I guess, where do you see the importance of quantum technology going? What is your projection of it?
I think quantum computing is definitely going to have an impact in this world. However, I don't see immediate impact, maybe in the next 100, maybe even 150 years or so, as human engineering is still far too fundamental to even embrace some of the quantum advantages we have. So I think in 100, 150 years' time, quantum computing could have impacts, maybe AI. You could imagine AI neural networks being much more powerful with the use of quantum computing, and so that's a potential route quantum computing could take us. Yeah.
And open the floor, any other questions from the audience?
I'd have gone to sleep. I don't know.
Or they're too shocked by all the questions. Lovely, there are no questions.
You see, most of the time, quantum computing algorithms are good when you have large matrix operations. Right? And now, let's say we're doing some regularization with a large factor function. If that degradation happens, have you looked at how the algorithms will degrade in their functionality if that happens? Or there may not be much of an impact on the performance of the algorithm?
Right, so just so I understood this clearly. So if noise is still a key factor that affects quantum computers, how will neural networks get affected by this? Or
how will the algorithm degrade?
Oh, how will the algorithm, okay.
Because that's the end result.
Mm-hmm. Right.
So if that happens, like if it degrades to a classical computer, how will my, let's say, large matrix factorization algorithm degrade?
Well, I'd say it definitely become much more slower. I think that's the biggest advantage quantum computer offers over classical computers, is that it's able to perform complex calculations in a fraction of a second compared to classical computers. So I'd say a big issue would be the algorithm would be slowed down. So that's one. Yeah, yeah. I think that's the biggest issue there. Thank you very much.